Hello, everybody. Welcome to another episode of the Observe Intelligence podcast. My name is Belyadi. I have a very special guest with an extensive background in machine learning with us today, Dr. Misra. Dr. Misra, welcome on board, and I would appreciate it if you could introduce yourself and tell us a little bit about your background.
Thanks a lot, Haas, for inviting me. And it took us some time to kind of get to today because of all these different things both of us are busy with. But good to see you. Good to talk to you. I'm an associate professor in Texas A&M University, and I've been here for almost 1.5 years. I focus, let's say, 90% of my effort on machine learning for oil and gas subsurface applications. And the remaining 10% of my interest goes into formation evaluation. So long time back, I started as a petrophysicist formation evaluation, close to 10 years back. And then slowly formation evaluation, the beauty of that field is it involves a lot of different data sets, a lot of different physics, a lot of different data. Sometimes you have really large data, and all these statistical techniques, regression methods, classification methods, already we as petrophysicists, we as formation evaluation people, we were using it. So that was, let's say, close to 10 years back, and slowly that led me to go into data science. And right now, all my effort, 90% of my effort is focused on machine learning. And in my work, I involve myself with activities from four different communities. So one is the SPE, the other is SEG, then AAPG and EAGE. So I'm kind of actively involved with all the four. Because I'm from a formation evaluation background, I sit somewhere in between petroleum engineering and the geoscience, geophysics world. So it's a very nice place to look at all these different things that are happening all around. So looking forward to our conversation, Haas.
Yeah. Thank you, Dr. Mishra. The first question that I like to ask is kind of an ask and high level question, and then dig into more in depth questions. So, given your extensive background in machine learning, especially in the oil and gas industry, where do you see the highest potential when it comes to machine learning applications, like especially field applications? I know you've been involved in a lot of projects, and if you could maybe touch on some of those, that would be greatly appreciated.
Yeah. So machine learning has a very important role to play in recovery of subsurface energy. And when I say subsurface energy, I mean hydrocarbons, I mean geothermal. I also mean sequestration under the ground. If you are producing energy, you will produce CO2. You have to capture the CO2, and then till we don't know how to use the CO2 properly, the best thing is to kind of inject it back into the ground. So subsurface has a big role to play in this subsurface energy world, and machine learning will help subsurface energy a lot. So I see three areas in which machine learning can help. The first one would be reservoir characterization. The
Mhm.
second will be field exploration and evaluation. And the third one, which is very important for both geothermal and hydrocarbon world, which is production optimization and recovery improvement. That's the final important fundamental that we need to address: how to improve and optimize production and how to improve recovery. Now, when we talk about reservoir characterization, how has machine learning helped so far? And from my experience, there are three areas in which machine learning is helping in reservoir characterization. The first one is where you want to detect and locate geological structures.
Mhm.
Um,
Mhm.
Subsurface is opaque. We cannot see anything. We have to use sensors, seismic sensors, electromagnetic sensors, and then we have to detect and locate geological structures. And machine learning have shown a huge potential in detecting those structures. The second is predicting reservoir properties. So when I say reservoir properties, I mean the physical or the chemical, the mechanical, the transport. All these properties can be predicted using machine learning. The beauty of machine learning is it can relate X with Y. Um, Depending upon how you define the Y, depending upon what kind of data you have, which will define your X, you can relate X and Y, and that Y can be the reservoir property. So when I say reservoir property, as I just mentioned, physical, chemical, mechanical, transport, all these properties have been predicted pretty well using machine learning. And the third thing is uh, whenever we deal with subsurface, the subsurface is nothing but geological material. It's a collection of a lot of different minerals, a lot of heterogeneity, a lot of anisotropy. So to detect these mineral constituents, where are the minerals, how are they distributed, and once we understand that, that will help us uh, create better engineering systems. So for detection and location of all these mineral constituents, machine learning is pretty useful. So what I just talked about is reservoir characterization. If we move into field evaluation, right? In field evaluation, we can predict. Just a second. So in field evaluation, we can predict the facies, the lithologies that are there. How can we do that? Using logs. Using logs, we can relate these logs to different facies, different lithologies. We can identify sweet spot. We can identify zones where there is frackable material. When you are developing a field or when you are trying to reach to that resource, you need to ensure that your drilling has very low risk. You are drilling at a very high efficiency so that you reduce the cost. So drilling efficiency, drilling risk evaluation, sweet spot identification, frackable zone identification, facies and lithology classification, all this thing will go into field exploration and evaluation, and machine learning has already shown a big potential in solving these problems. Now, one final thing when I talk about production optimization, in production optimization, the biggest question plenty of times what we deal with is where should we place the well and how can we optimize the well placement and well completion. When we are trying to address the damages in the wellbore, we want to remove the damages, we first need to understand what is the condition of the well. So all these things can be achieved through machine learning. So what I just tried to show you in just this last 7-8 minutes of my monologue is to show that machine learning can be applied at each and every level in subsurface energy engineering. And it is up to us as engineers, as scientists, to design all these different interesting applications.
Absolutely. Yeah, like you're basically saying using your domain expertise to find what problems we can solve and what is the value proposition of these problems that we can solve, which is a great point, you know. So based on all of these projects that you have been working on, like I'm sure you always notice the pros and cons, you know. So what are some of the shortcomings of some of these machine learning projects that you have worked on in the past? Maybe if you can touch on a couple of examples, that would be great.
Yeah, so when you say shortcomings, right, the biggest shortcoming from my point of view
Hmm.
arises when we don't have data. And there are so many occasions when we don't have enough data. So when I say data, we need data that has enough statistical distribution, enough statistical variation so that you can understand your data better. Plenty of times when we are trying to solve a particular task, the data itself might not have enough variation. And if your data doesn't have enough variation, anything that you develop using that data will be biased. What I mean by that is you cannot apply it to any future work because your data has seen a very limited behavior of the system that you want to explore. So to that, what I would like to add is a lot of engineers, a lot of scientists in the geology, petroleum, geophysics domain, they are getting tempted to jump into data science, to change their career completely to data science. To them, what I say is data science comes at a very high level in the sense the most important thing to begin with is how can we engineer a system. So engineering the system is the most important thing. If you cannot engineer a system, you will never capture any data. So to engineer the system, you need geology, geophysics, and petroleum engineers to work together, or the subsurface engineers to work together. So you engineer the system. And then what you need is sensors. So you need companies, service companies like Schlumberger, Halliburton, they have to bring in their expertise and they have to deploy the sensors. And it's only after that you can get good data on which you can do data science. So that's one of the biggest challenge that any machine learning that we as engineering companies or engineering discipline do. It depends on data that needs to see the physical system accurately. And to see the physical system accurately, you need to ensure that you engineer the system properly and you need to deploy good sensors. If you don't have that, anything that you develop using machine learning will not be generalizable. What I mean by that is you can develop it for one case, it will never go and get applied to some other case.
Some
So
mindset.
that's the biggest problem that I face.
Got it. Got it. No, that's very good. And I think that's also one of the limitations that we have. Like a lot of times, we can the distribution of some of these features are not, it doesn't have enough like variance in the data set to build a general model, like as you said. So a lot of people develop these overfitted model where it memorizes these trends, and then as soon as you apply it to a blind set, it just doesn't hold anymore. So that's very valid. And I think that's a problem that the industry has, and I think it's always going to be a challenge. So and that's when you decide whether we should use machine learning or other like approaches, to solve
Yeah.
that problem.
So to that, what I would like to say is machine learning. I'm not talking about AI because AI is something very different, very broad scale. I'm talking from an engineering point of view, and from an engineering point of view, I see a lot of use cases of machine learning. So everything that I say is with respect to machine learning, which is using computers to learn to do a particular task, right? So from a machine learning point of view, uh, machine learning is suited for processes that are beyond rule-based approaches, or they are beyond algorithms. So what I mean by that is if you can define the rule of doing a particular task, or if you can write an algorithm, then you don't need machine learning. What I mean by that is if you know the first principle of a particular process, you don't need machine learning. You need machine learning when the system or the process that you're trying to understand or trying to model is complex, heterogeneous.
Mhm.
It has behavior that are emergent and hidden. So I used four terms, and these four terms are very different: complex, heterogeneous, emergent, and hidden. So
Mhm.
if your system is like that, if it has behaviors which are like that, then machine learning is best suited. But if your system is not like that, then machine learning cannot give you any added advantage. You can do those things using simple physics, simple statistics, or a simple rule-based code. And another very important thing when machine learning outshines is when you have multimodal sources. So what I mean by multimodal is when I talk to you, I'm using my hands, I'm using my facial expression, I'm using my voice. My voice has modulation. So there are a lot of different ways in which I'm trying to communicate. So if your system that you want to understand is being measured or is being sensed using a lot of different sensors. Let's say some physics-based electromagnetic sensors, some acoustic sensors. There might be some other type of pressure sensors. So this is a multimodal source. And when you have multimodal source, that multimodal source is generating large amount of data at a very high rate, and that data is unstructured.
Mhm.
Unstructured. That's when machine learning shines. If your data is unstructured, machine learning will help you identify the structure in the data, and then you can use that structure to better discover new knowledge or to automate a task by handling complexity.
Got it. Got it. No, that's a very good answer. That's a very good answer. So I always ask my guests about their vision, in terms of the future. And given your extensive background, what are some of the breakthroughs that you foresee in machine learning in the oil and gas industry?
So this is a very tough question in the sense, I'm from academia, and in academia, we try to break the frontiers in terms of the fundamental aspect or applied research aspect. In academia, mostly what we do doesn't have any commercial angle. So my answers may not help from a commercial side of things. But if you talk about the frontiers that needs to be overcome when it comes to subsurface energy or subsurface engineering, um, the first challenge that we are facing right now is availability of data.
Mhm.
It's not just academia, service companies, operators themselves, they face uh, challenges in terms of getting good quality data that can be used to automate something, right? So how can we obtain good quality data? So the first approach that a lot of companies are taking is to augment data generation. So they will get some real data, but that data is small. They will use that data and expand their data set by creating synthetic data. So now they have a much bigger data set, and then they will create machine learning algorithms uh, on this bigger data set, which has a lot of synthetic data in it. How was the synthetic data generated? There are a lot of different ways in which you can generate synthetic data. One approach is simulation augmented synthetic data generation. So you're using simulation to generate synthetic data. But again, your foundation is the real data. Why are you doing all this? Because you don't have enough data. What will you get out of it? By having a larger data set, that's when machine learning will outshine, right? So that's one of the challenges that needs to be overcome, which is how can we create more realistic looking synthetic data, which can help machine learning. The second way in which a lot of companies are trying to break barriers is they're trying to create open platforms or open portals where data from different companies, different architecture can come in and become one standard data set on which machine learning can be developed. So this is another way in which it helps cross barriers, integrate disciplines, and make the data set more usable across a lot of disciplines. So that's another approach. Now, I'll say this thing once again, which I mentioned in my previous answer, which will help address one of the frontiers. So one of the frontiers that all of us are facing is your goal is to engineer good subsurface systems. To engineer good subsurface systems, you need to deploy sensors that can measure that system. And when you apply these sensors, they will generate a lot of data, and you can do machine learning pattern recognition on it with a goal of improving your subsurface engineering system. So in this, there are three layers: engineering the system, deploying the sensors. A lot of times we ignore these two systems. We think that data science will solve everything, but that's wrong. For solving important high profit problems, all these three things needs to be brought together, which is how you engineer the system, how you deploy the sensors, and then you perform data science. You cannot do only data science. So this is for all these engineers and geophysicists, geoscientists who think that moving to a completely data science world is the solution. No, it is not the solution. Engineering science is the foundation on which sensors come in, and then comes the data science, which is the third layer.
Yeah, a lot of people try to skip those first two steps and move to the last step, which usually doesn't work that well at the end of it, So
okay. Yeah. So in terms of what is popular these days when we use machine learning, there are four areas from my point of view which are very popular in engineering world, and this is true for oil and gas. This is true for other engineering aspects. Number one is anytime we want to automate mundane, repetitive, low risk tasks. That's where a lot of machine learning applications have gone into automating mundane, repetitive, low risk tasks. The second is if you want to continuously improve your strategy or how you solve a problem, if you want to continuously improve, you need to create a data channel that can bring in a lot of data, and you will continuously improve your model or your system so that you can continuously improve your strategy. So if you need continuous improvement, machine learning is one way. The third is If you want to detect minute patterns, small patterns in a high dimensional data set, machine learning pattern recognition methods are the way to go. Why do you want to detect these minute patterns? Because these minute patterns contain information about your system. For example, fraud detection. Fraud detection looks at minute patterns of fraud. Similarly, we can, in engineering world, we can detect damages. We can detect uh, things that are anomalous, and these are very minute patterns, and they need to be detected using machine learning methods. And if you want to do precision engineering, what I mean by that is, if what you want to do at depth 10,000 feet, if that needs to be different than what you want to do at a depth of, let's say, 9,500 feet, there's a small gap of 500 feet between these two depths, but you need to precisely engineer these two depths. And how you engineer these two depths are different. And if that's the case, then you need machine learning to help you perform precision engineering. So these are four popular areas where a lot of machine learning effort is going into.
Going to. Got it. Got it. Thank you for clarifying that. And then, as you know, there have been a lot of research papers, books. You have one of them yourself on primarily like the applications of supervised when you have your inputs and outputs, unsupervised for clustering. Some people use like semi-supervised. There are a lot of papers and books and like on these approaches. But one of the approaches that I've noticed that hasn't been as popular or hasn't had too many applications, at least in the oil and gas industry, has been the reinforcement learning. Can you touch on, what is your vision for reinforcement learning? Uh, you know, like like in terms of the oil and gas industry.
Yeah. So the first thing that most of us learn when we are new to data science is supervised learning. And what is supervised learning? You have X and Y, and you want to relate X with Y.
Mhm.
Uh, Initially, when I was new to data science, machine learning, I thought I did something amazing or something very important when I solved supervised learning problems. But more time that I spent in supervised learning, I've learned that relating X and Y is very easy. These models are designed to relate X and Y. You give it a X, you give it a Y, they will relate it. That's supervised learning.
Mhm.
And when I look back, what I'll say is supervised learning is very, very, very easy. The problem with supervised learning is, how do you ensure your X is good? How do you ensure your Y is good? How do you ensure that the model that you develop will be applicable to the new data set or a new system? So that's supervised learning. From my point of view, it's relatively easy. The next stage is unsupervised learning, which is very difficult because you don't know what's the right solution. Unsupervised, you don't know what you will discover. What's the beauty of unsupervised learning? The beauty is it can help you discover new knowledge, new insights, new information. So, for example, in one of our unsupervised learning work, we were able to detect a signature that is indicative of a particular type of fracture. So when a fracture is produced, a sound is produced, you can measure that. And when you look at the waves, waves will look like squiggly line. You cannot make any sense. And then unsupervised learning helped us figure out a pattern that is that has the most information about the type of fracture that was created. So that's a very good use of unsupervised learning, creating new knowledge, finding new knowledge. But it's very difficult. That's what I tell my students. If you actually want to outshine your competitors, you have to be very good at unsupervised learning.
Mhm.
And why unsupervised? Because that will help you find new knowledge.
Mhm.
And the most or the hardest way of learning is reinforcement learning. Uh, it is very difficult. And if I'm correct, do reinforcement learning when supervised learning fails. If you cannot solve the problem using supervised learning, that's only when you should do reinforcement learning, because reinforcement learning is very hard. But the beauty of reinforcement learning is the learning is the closest to natural learning.
Mhm.
So for us as animals, as humans, uh, the way, how do we learn? We learn by exploring the environment. Initially, we don't know anything about that environment. We do a stuff, and then we get a feedback, and then we decide whether to do that stuff more or less, right?
Mhm.
For example, when we write a paper, we don't know the quality of the paper. It's only when we get feedback from the reviewer, that's only when we know the quality of the paper, and then we decide whether we should write more like that or less like that. So that's what reinforcement learning is. You are continuously interacting with the environment, and you're learning from the environment to do a particular task. In my reinforcement learning work, I have tried to solve two problems. And in both the problems, we are interacting with virtual world or numerical simulation. That's the world that we are interacting with. But what we have shown is if you can work with numerical simulations, you can actually work with the real world. But in the real world, you should allow failure. So if you can allow failure to occur, then you can take this method that we have developed and deploy it on the real world. But coming back to what we have developed, so there are two problems that we are trying to solve using reinforcement learning. The first one is, can we accurately predict how is the variation of permeability as you go away from the well
Mhm.
using reinforcement learning methods? So this is like automated history matching or assisted history matching, but we are using concepts of reinforcement learning. So when I say concepts of reinforcement learning, there are two neural networks. These neural networks, one of them is learning how to take an action, which is how to change the permeability around the well. And the other one is criticizing the actions taken. So there's
Mhm.
an actor and there's a critic.
Critic.
And both of them are learning. One is acting, one is providing feedback, and they are learning how to place this, how to create this permeability that satisfies a production history or a volume rate history. So that's one approach. It is very difficult. In our latest work, what we have shown is we can apply reinforcement learning on a very simple case.
Mhm.
But as we increase the complexity, things get more and more difficult. The other idea that I'm very passionate about, and pretty soon we'll be publishing a paper on it, which is how can we control um, fractures using reinforcement learning. We have shown that it works in a simulated environment. If somebody is interested, we can then deploy that system that is learned from simulated environment directly on a real world environment. And both these examples are reinforcement learning, which means we are continuously taking a feedback from an environment. There is no data, there is no right and wrong. We are taking a feedback, we do an action. If the action is good, we'll get a feedback, or else we'll have to repeat.
Huh, that's yeah, I'm actually very interested on the second one that you mentioned on controlling fractures, controlling the hydraulic fractures. I'm very looking forward to see that paper actually when it gets when it gets published.
Yeah,
Sure, and I'm sure. I mean, it's a very important topic, and I'm sure a lot of the operators might have some interest in that as well. Especially if you can, especially if you can couple that with like real time applications.
mhm.
Which takes me to the next question. So the next question is, are you bullish about the real-time machine learning applications in terms of either in drilling or hydraulic fracturing, like I know that like a lot of like the models that have been developed in the past have been pretty static. You supervise learning to understand trends between the inputs and the output. You do clustering analysis using unsupervised k-means, hierarchical, whatever algorithm you use. I think in the next few years, there's going to be a lot of interest in real time machine learning applications. So I wanted to see, as somebody who's been involved in a lot of these projects and have been involved in the academia for a while, what are your visions, in terms of real time machine learning applications in the oil and gas industry? Maybe you can continue on your previous thoughts
Yeah,
on controlling the hydraulic fracturing.
yeah. So real time, right? So your the way you asked your question, which is you move from reinforcement learning to real time, that's a very nice transition because reinforcement learning in the real sense is real time. You're taking real time feedback from your world. So let's say there is one approach that we are trying at this point of time. Maybe all of you will resonate with it. So let's say you're injecting a fluid into a well, and you're injecting a fluid. You want to create the fracture. So when these fractures get created, they will create some acoustic emissions. You can record these acoustic emissions, and the more you inject, the more acoustic emissions will be created. The patterns will change because your material is changing. As you're creating fractures, you're actually changing your material. So it's a very dynamic problem. What I mean by that is your system is changing because you're creating fractures, and it's a very complex way in which it is changing. You cannot analyze the system, let's say, after 10 hours. You have to analyze the system real time. Let's say every minute, you have to make a decision. You have to understand your system, because if you don't do that, then all this data gets more and more mixed. So for a real-time application of machine learning, you need good sensors that can detect in real time. If your sensors are not good, if your sensors measure one day at a time, then it will be very difficult. So what kind of sensors are most suitable? So any kind of sensor which are pressure transducers, they're very sensitive. You can make some real-time assessment with it. So coming back to your question, which is what are the applications of real-time machine learning? To that, what I'll say is, what kind of real-time sensors do you have which can actually measure high quality data? Okay, so let's say you have good sensors that can measure in real time. What happens after that? After that, we have two approaches, and I would like the listeners to reach out to a scientist. His name is Dingzhu Cao, CAO. I think he's right now with Devon. He was with WPX. I'm taking this idea from his work, which is once you have a reliable real-time sensing system, you can perform edge computing on it, or you can perform edge stream processing. So if you follow his work, that's where he has shown the power of real-time machine learning using these two approaches. So edge computing is a slightly older concept. Edge stream processing is slightly new compared to edge computing. Both of these approaches can help you achieve real-time machine learning. Dingzhu Cao, you can reach out to him. He was in WPX and right now he's in Devon.
Yeah, we can put his contact at the bottom of this.
Yeah. So the reason I'm mentioning his name is because from my point of view, real-time machine learning has been neglected, as you just mentioned, and he and his team, they have done a great job.
Yeah. And there's a lot of potential because like a lot of the operators, like, you know what, we understand that we can find insight, find patterns in the data, you know, but I don't want to wait until the well is drilled. I don't want to wait until the well is fracked. What can we do real time to adjust, you know, using those edge devices that you mentioned and make those adjustments, you know? So I think that's good. Thanks for sharing him. Yeah.
If your system can be imaged or mapped using, let's say, some kind of a optical sensor or some kind of a seismic sensor, if you can image it, then only you can perform some real-time control or real-time changes based on machine learning. So the crack, the work that I mentioned of controlling crack, the reason we can do that in this work, which will be published, is because we can image it, which means we can see it. It's an image. But can you do that in subsurface? That will depend whether you can image it, because unless you understand how things are changing accurately, you cannot control it. Or even if you try to control, you will control it in a very weird way, because reality is like this and you are thinking it is like this, and the whole control will go haywire if you don't see it properly. So you need very good sensor deployment to achieve the control.
Got it. Got it. And then it'd be unfair, like it'd be like very unfair to go through a whole podcast and not talk about your book. You have a book called Machine Learning for Subsurface Characterizations, which was published, I believe, in 2019.
Yes.
I'm sure like the audience would love to read some of your thoughts, and I'm sure you have a lot of great chapters in there. Maybe can you touch on, like, walk us through some of the contents in that book and what the readers could gain from getting the book?
Yeah, so that book was published in October 2019, and we are right now in 2021, right? So 1.5 years has gone by already. My emphasis in that book was to explain fundamental concepts
Mhm.
of supervised learning, unsupervised learning, data processing, feature extraction, feature creation, which is the foundation. So I explained all these foundations using some case studies. So that book, if I remember correctly, it has 12 chapters, I think 13. So there are 13 chapters,
Mhm.
and each chapter is different. Each chapter looks at a different case.
Mhm.
Some case studies are very applied. Some case studies are abstract, which means if you apply a particular engineering thing, this is the data, how the data will look like. So there are few chapters which are slightly abstract, and there are few one or two chapters which are based on experimental data. And in all these chapters, the focus is foundation
Mhm. Mhm.
foundation of how should you perform the scaling, how should you perform feature extraction, how should you check your supervised learning. If you're doing unsupervised methods, how do you what do you say, quantify the quality of your clusters of the or the quality of the structure that you found. So from the reason I wrote that book is to share with the readers the foundation, and I'm very happy with that. But pretty soon, I think I'll have to come up with another book which is very applied, which can stand the test of time, which
Mhm.
will have codes in
Mhm.
it. And I think your book, which I think will be published pretty soon, also has those aspects, right?
That is correct. Yep,
Yeah.
that's correct. Yeah, we have the Python codes. We have the
Mm-hmm.
like the applications, and then like followed by the code, so people can actually replicate it.
Mm-hmm.
But I'm
That's
sure. Yeah,
Yeah, that's very important. So your book, it covers a lot of different petroleum engineering applications, right?
correct. Yeah, we have, I think, 15 examples on
Uh-huh.
completions, drilling optimization, like production optimization,
Yeah,
on some of the applications on geoscience. Uh,
lovely. Okay.
yeah. So, but hey, I mean, I think the more books, the more papers that we have out there that
Mhm.
those can follow,
Yeah,
the stronger we would become as a community. So I would love to see another book by you. That can touch on more in-depth concepts and actually show the either Python or R, or
yeah,
whatever
yeah,
programming language that you
yeah.
prefer. I know
So,
there are a lot of
yeah. So one thing a lot of readers complain is that your books are expensive. But again, I'm not the person who decides the price of the book. I'm the person who works really hard, just like you. We work really hard. We write that book. What's the main objective? The main objective is to share what you know,
correct.
to take the whole community with you, and hopefully one day you will also learn from your community, right? So the community gets better, you also get better. So
Yeah,
that's why I write books, and
yeah.
the final prices are decided by
Publisher.
the publisher, and that's the price that they have decided to go with. So don't complain. I'm not. Yeah, that's not the intention. Our intention is not to become rich by publishing such books, because these are technical books. The whole goal is and writing a book is so difficult. You can only write it if you love a particular aspect of it.
Yeah.
So recently, or in April 2021, which is almost in a month, I'll have my second book out. But this second book is all about use of electromagnetic sensors, or use of electromagnetic methods in the subsurface,
Mhm.
how we can better analyze the electromagnetic data, how can we understand wettability, saturation, and so on. So it's a book totally focused on electromagnetic methods, which is one of the things that I love. in terms of sensing, I love, I have spent so much of time on electromagnetic sensing till date. So that's why I'm writing the second book, and it's ready to be published by April 2021. And it will be with the same publisher, and it will be expensive, sadly. Yeah.
We can put the links to all these books, for for the audience that have any interest in to go and actually get it. And I always tell people I'm the same way that as authors, we don't write book to make money. That would be a terrible idea because the goal of like writing these books, I always tell people, is just to educate people, because I have a lot of passion myself for writing. I
Yeah.
enjoy writing. I do it as a hobby, so
And yeah, one of the things that helps me a lot when I write a book is, personally, I put everything in a logical structure.
yeah,
So my brain gets better when I write such books. I understand what I'm writing, my concepts even better, because now there's a logic, right?
mhm,
So
mhm.
personally, writing book has helped me a lot in
Absolutely.
terms of understanding my concepts, understanding what I'm doing better.
You have to understand it to write it and actually
Yeah.
explain it well to the audience, yeah, the reader. Absolutely, absolutely. And also, one final question. And I appreciate your time today. What are your final thoughts, recommendations for people starting out? You probably get that question a lot, especially teaching at Texas A&M. Maybe you can give some recommendations to some of the younger audience that we have, like as far as what do you recommend them to do? Like as far as if they're trying to get started in the field in the field of like machine learning, what are some of your recommendations on that?
Yeah. So when students they start uh, in the area of machine learning, um, what I always encourage my students to do, and when I say students, these are undergrads, mostly undergrads. There are graduate students as well that I supervise in research, but I'm not talking about the research side. I'm talking about, let's say, undergrads who
Mhm.
are there to learn a skill and then apply it in the real world. So what do I tell them? So the first thing that I tell them is, don't get lost, because there's so much of information that's out there. You
Mhm.
have to streamline, you have to kind of focus narrowly. If you don't do that, you will get
You get lost.
really confused. Why? Because you have so many different programming languages, so many different platforms, so many different ways of doing the same thing, and so on. uh, uh, so if we just talk about machine learning, then the first recommendation is supervised learning. Start with the easy job. Now, in supervised learning, how can you go about learning to write code? So for that, what I recommend a lot of the students to do is to go to GitHub or to go to Kaggle, try to see what kind of codes are available for simple supervised learning methods, and then get those codes and try to do something similar
Mhm.
on your own data set. How can you get your data set? Oil and gas data sets right now are available at a lot of different places. There are a lot of states which provide these oil and gas data. There is Volve data. There is one that is coming from SPE as well. So you will find simple data to work with.
Yeah.
So get inspired from all these different places and then apply it on your own data sets, and start with supervised learning. Let's say spend close to 6 to 8 months on supervised learning. Once you get comfortable, then you move on to unsupervised learning. And as you're doing this, stick to one programming language, one uh, set of packages. So a very reliable set of package would be sklearn, matplotlib, pandas.
Mhm.
These three are good enough, NumPy, and then you select Python as a language. Don't get confused whether you should go for R or Julia or Python. Python is doing pretty well right now, so just stick to it. Uh, so this is something that I tell them. I tell them this thing, that you cannot learn machine learning by reading books. You cannot learn it by reading or watching videos. You
Mhm.
have to do it,
You have to do it. Yeah.
and to do it, you can do it on your personal computer. It's such so easy.
Mhm.
And always think, can you apply it to the data set from your world? Your world, as in, let's say you're a petroleum engineer, your world will be the production data, the volumetrics, and so on.
Mhm.
If you're a geophysicist, your data will be seismic data. So get inspired and then apply it to your own data.
Yeah.
And have a web presence, have some kind of a web portal or a Google web page where you can put these codes, or you can put the video demonstrations that help you explain these things. One final thing to everyone, and especially the young folks, data science is not everything. You are blessed to be engineers. You're blessed to have been selected this field of engineering or the science. Geoscience is also a very good field to be in. Geophysics, so geoscience, geophysics, geology, petroleum engineering, or some kind of subsurface engineering. If you have chosen this field, don't leave it. Decide how you can engineer the system, which is your subsurface system, how you'll deploy the sensors, and then you will perform data science on it. Don't go to data science because that space is hollow. There's nothing below it.
Mhm.
So you have to start from here. You have to build things from the top. If you try to build things like this, then you are losing this beautiful opportunity that all of you have, which is domain. Domain is the system that you're engineering, the sensors that you're deploying, and then is the data science.
Data science. Very
Yeah.
good. Wow.
So don't leave. Don't leave the domain that you have selected.
Yeah, yeah, no, that's very good answer. Very, very different than the answer that I usually like receive from the guests that I invite. So again, it was such an honor, like, and pleasure to have you today, Dr. Mishra. It was very informative. I've personally like learned a lot, so I appreciate your time. I know you're very busy, you got a lot going on, so I appreciate you accepting me on this podcast. Uh,
Yeah, thanks a lot, Haas. What
yeah,
you're doing is very good. You're bringing the community together. Not a lot of us are doing this. You are doing it in the technical domain. It takes a lot of time from you to arrange all these things and then go into discussion. But this is a great job that you're doing at this point of time, and you should continue. There are not many like you who are doing this. So all the best for you, and hope to kind of meet you in person someday soon.
sure. Thank you so
Yeah.
much. I appreciate you. Thank you. Thank you so much. And thank you, everybody, for listening today. I hope you enjoyed it. If you enjoyed it, please like and share. And see you next time. Thank you so much.
Take care.
Thank you.